A practical approach to tunnel design for fire loads. With more and more underground and tunnel projects are now being implemented around the world for public transport, there is ever-increasing demand for ensuring safety and adequacy of tunnels during its whole life cycle. Design approaches to tunnel is now quite advanced with availability of numerous finite element software, but recent incidences of fire in tunnels raises a serious question about tunnel safety in fire. Though the risk of fire incident in tunnels is significantly low, however, it can sometimes be catastrophic considering its impact on losses of life, disruption of services and economical losses in adjoining areas. Last decade, engineering community has come up with of solutions, which not only mitigate risk from fire, it also ensures that passengers are safely taken out and structure suffers minimal damage, so that tunnel can be put into services with minimal efforts and cost. What happens when fire catch up inside a tunnel? Underground structures are mainly confined space, which leads to imperfect combustion due to the lack of oxygen, produces larger amounts of smoke and poisonous gas. Since this occurs in a confined space, there is a limited capacity to remove heat and smoke, and temperatures rise quicker in underground spaces. Further escape routes are also narrow, long, and have limited visibility due to smoke. This increases the dependency on emergency lighting and evacuation signs. In addition, it is difficult for firefighters to judge the extent of a fire in an enclosed space. This means fire risk mitigation during the design phase is vital. One of the biggest underground fire incidents was Mont Blanc tunnel fire in the year 1999. It became a turning point of discussion for the improvement of fire safety in underground structures. It caused the loss of 39 lives and major damage to the tunnel structure and equipment. It was shut down for 3 long years. While this fire was linked to an accident, some fires were the act of sabotage. One such example is the 2003 arson attack in Daegu, South Korea. In February 2003, a man set fire to a coach in a subway train using volatile materials. The death toll reached 192 and 148 were injured. It also led to property damage costing over $40 million, Hong, 2004. The tragedy revealed many flaws of the Daegu metro system, such as very poor visibility of the emergency lighting due to smoke obstruction and electricity power outage, Hong, 2004. Behavior of concrete under fire. The behavior of concrete under fire exposure is determined by the properties of the aggregates and the cement matrix, its moisture content, pore structure, and loading, in addition to the rate of heating and maximum temperature attained. When heat penetrates concrete, it results in desorption of moisture in the outer layer. Most of the water vapor formed will flow towards the cold interior of the concrete and be reabsorbed in the voids. As this process continues with heating and once the saturated layer cannot move fast enough through the pore structure, it is overtaken by the advancing heat front, which causes the water to evaporate at the interface, and due to the rapid rise in temperature and the restrained expansion, the vapor pressure rises rapidly. When the pressure starts pushing outer layers, spalling of concrete happens. The reason behind this spalling can be attributed to tensile strength of concrete subjected to vapor pressure excreted on concrete. It is observed that concrete with high strength, low permeability is more prone to this mode of failure, particularly if they have a high internal moisture content. Causes of fire in tunnel. If we investigate, the major fire incident occurred due to poor maintenances of electrical system. While mechanical system failures related incident causes smaller fires. Other major reason is arson/explosion. Data from DO, BL, 2007. Statistical analysis of the foreign underground fire accidents cases. Fire science and technology. Breakthrough in design. Last decade worldwide, engineering community has made significant achievement in developing advanced and sophisticated liner design along with reliable fireproofing systems and use of artificial intelligence. Onset, the whole activity was targeted to provide passengers with a safe, smoke-free egress/escape tunnels, thus reducing loss of lives, ensuring that the structure can still withstand major service loads during and after a fire. Better quality control to minimize explosive concrete spalling and detrimental impacts of fires to the tunnel main structural components. Ensure that any damage is reparable, so the facility can return to normal operations as rapidly as possible, thus minimizing economic impacts. Application AI to develop systems which can early detect fire in real time and reduce response time and ensuring safety and losses both lives and economy. The minimum legislative level of safety for structural fire design aims to provide an acceptable risk associated with the safety of tunnel, firefighters, and people in the proximity of it. It is on owner's acceptable risk depending on tunnel size, clearance envelope, provisions for facility systems, supporting equipment, emergency egress layout, as well as the entire adopted emergency egress scenario. All will be determined based on the initial classification of the facility. Latest trend is to use sophisticated experiment to develop project-specific fire curve based on usages and characterizes of tunnel to access effect on tunnel liner and requirement of protection system. Alternately, of course, standard fire curves, such as the Reichswater State, RWS, or ISO fire time temperature curves, are still valid and many engineers use them when no additional fire engineering/data is available or planned. While deciding the requirements of structural fire protection system and its type should be chosen careful consideration especially for those locations involved in any safe haven or rescue. The risk study should consider the likely fire size and its thermal impact on the type of structure involved, heat transfer, smoke leakage, structural damage, spalling, etc., and the consequences of structural failure. Appropriate temperature development curves should be chosen for the testing of the materials involved. The standard temperature curve such as the ISO 834 fire resistance tests elements of building construction should be commonly used. Where high fire temperatures are possible, e.g. petrol fires, other test curves should be considered. Choosing appropriate fire time temperature curves. Recent trends in large projects is to carry out project-specific assessment. Customized fire curves are gradually considered as the industry norm with an increased focus on an actual fire event that a tunnel should be designed for, based on the type of the vehicles and their combustibles that are allowed into the tunnel like rail/metro or roads. As there are differences in causing fire either by combustion or electrical or any other reasons. Once we identify the exposure and risk associated, customized curve provide best fire loads the tunnel shall be designed. Now, Eurocodes provide advanced calculation methods and guidance and using performance-based engineering allow for a more prudent approach to fire protection, which generally based on detailed quantitative and qualitative risk assessment for a fire event in a tunnel. The Eureka curve proposed number of fire time temperature curves proposed for a variety of applications, ranging from the ISO 834, 1975, cellulosic curve to the RWS curve, figure. The selection of an appropriate time temperature curve and the relevant fire duration is an important consideration, which should be driven by a risk assessment, in cases where no design standards apply. Once a suitable fire time temperature curve has been selected, the likely effects of such a fire on the tunnel's structure should be ascertained. European Standard N 1992-1-2:2004 provides methods of calculating the reduction of concrete strength due to high temperature damage within the concrete and its steel reinforcement. N 1992-1-2:2004 also provides guidance on the reduction in the cross-section due to fire damage and subsequent structural stability checks. Active fire suppression. Suppression systems are now viewed more favorably than before, in terms of their asset protection and life safety benefits. The key issue is to control any fire spread, by early application of water at the affected tunnel locations. NFPA 502, 2008, deals with water-based fixed firefighting systems in road tunnels. It concludes that such systems should be considered where an engineering analysis demonstrates that the level of safety can be equal to or exceeded by the use of water-based fixed firefighting systems and is a part of an integrated approach to the management of safety. Here, engineers quantify heat transfer from hot gases into the liner and calculate temperature distribution within structural elements over time, using sophisticated finite element modeling that account for changes of the tunnel liner material properties, concrete and steel, due to heat exposure. The analyses assess the liner's spalling potential, its load-carrying capabilities, and its potential deflection. On completion of these analyses, if it found that a sacrificial concrete layer is adequate to protect the tunnel liner and that the temperatures in the reinforcement and the concrete remain below 250 C and 380 C, respectively, as required by NFPA. In such cases, structure is stable and not significantly affected, no fireproofing protection system is required. Owners normally prefers to protecting their tunnel's structural integrity from fires using the sacrificial concrete protective cover due to its constructability advantages, the fact that it is maintenance-free and its inspection falls into the pattern of regular facility inspections. Additional reinforcement, if required within the additional sacrificial concrete protective cover layer, usually outweighs the costs of a separate fireproofing material and the costs of its periodic inspections, maintenance, and replacements as needed. Polypropylene fibers. An effective measure to control spalling is the use of micromonofilament polypropylene fibers added to the concrete mix. The polypropylene fibers melt at 160 degrees and thereby increase the porosity of the concrete, enabling the dissipation of pore pressures. Consequently, no or very limited spalling occurs. Following a fire event, a risk assessment should be carried out to determine appropriate measures to be taken where the fibers have melted. The assessment should include at the very least consideration of strength reduction of the heat-affected concrete and required structural capacity permeability of the remaining concrete and the impact this may have on corrosion or other deterioration mechanisms. Risk of concrete spalling over time. The associated overall repair costs are relatively high. In addition, the tunnel cannot remain operational during the repair works. Panels. Effective passive fire protection can be provided by proprietary boards formed from calcium silicate aluminate materials, which can be post-fixed to the structural lining or used as false shuttering during casting of the concrete. A steel frame may be required to provide a clearance behind the secondary lining, for water ingress and inspection, for example, but this can prove to be expensive in terms of cost and installation time. Cementitious coatings. Passive fire protection can also be provided by applying a cementitious coating. The materials primarily consist of Portland cement with fine aggregates and can be applied in varying thicknesses ranging between 20 mm and 40 mm. The required thickness depends on the design fire load and the required temperature at the interface between the barrier and the concrete of the structural lining. The coating can be designed such that the temperatures at the face of the structural lining do not exceed 350 degrees Celsius, which will prevent spalling and significant changes in the mechanical properties of the concrete. A small diameter coated reinforcement mesh might be required to fix the coating to the structural lining. Protective coating, which is spray applied on the structural lining, undergoes chemical changes during the fire event. Therefore, it can only withstand a single fire, after which it has to be removed and replaced. The structural concrete is deemed to remain undamaged. An example of a rail tunnel with a cementitious fire protection coating is the 8 km long Grainhart tunnel in the Netherlands, which contains both cut and cover and board lengths. The average depth of the coating is 42 mm, designed to protect the structure against a 30 MW fire heat release rate. Conclusion. By developing project-specific fire curves, assessing each fire event for its specific features, assessing the structural durability of the tunnel liner for a project-specific fire, and incorporating proper fire suppression methods and operational aspects, engineers are well equipped to design safer and more cost-efficient tunnels.